Yeah, so it's okay break, but I'm for some reason really exhausted. So yeah, if I fall asleep, just wake me up and I'll get back to it. Okay, so today we're going to be talking about subsequences. Previously we were talking about sequences. Now we're going to be talking about something very simple, but also something really important, subsequences. So you know what a subsequence is, right? Like if somebody gives you a sequence and says, what would be a subsequence of this sequence? You probably intuitively know what that is, right? It's going to be some, like if this thing looks like A1, A2, A3, A4, A5, blah, 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 it's going to be some selection of those guys in increasing order, right? It's going to be like, maybe you take the odd guys, maybe you take the even guys, maybe you take, some sort of, anyway, it's going to be some selection in increasing order of that sequence, right? So the formal definition is, right, you have a sequence, P sub n, a sequence, and if you have given a sequence of a strictly increasing sequence, n sub k of natural numbers, then we call P sub n sub k, as k ranges from 1 to infinity, a subsequence of P sub n. Okay, I hope that makes sense, right? The n sub k is simply the selection of indices, right? This would be your n1, your n2, n3, blah blah blah, and then you just make this new sequence, where the index of the sub-index here increases, right? So P sub n sub k, right? So right, so. Yeah, so let me just start off with a simple observation. So observe, P sub n converges if and only if every subsequence converges. Okay. P sub n converges if and only if every subsequence converges. The backwards direction is clear because you could take this for the subsequence n sub k just being k, right? And then that would give you the full sequence. So the sequence is a subsequence of itself. Okay, so that's just take n sub k equal k, take n sub k equals k. So if every subsequence converges, then the original sequence converges. Right. So let me ask you just to remind yourselves of what convergence means, to try and write it down properly. How do you say that if the sequence converges, then every subsequence converges? So like take a subsequence, P sub n sub k. Okay, and then you need to prove that since this guy converges, write down why the other guy converges. So you'll have to remember what it means to converge, in case you've forgotten. Okay. So take like 3 minutes. 3 minutes and write down something, and feel free to talk with each other.
She said the sequence of n to infinity is contained in the neighborhood of so oh, well,
for the nth
high with they're seasonal. Well, so you take the epsilon of the convergent, the question is take the neighborhood and like you know, and so you're going to get every you have this the question would be like, now that you have this, okay. That's not necessarily true. I feel that, right? If the event converges, every subsequence theoretically should converge. Like say you have right? Because after some point and big N, then there's always a little neighborhood, but your index goes to infinity, your n to infinity. So after whenever you pass that n, whenever you pass like big N in terms of a little, it's still all within that same neighborhood.
Okay, does anybody, so somebody just first remind me, of the definition of convergence. Harrison?
For every epsilon greater than 0, there is a natural number n such that if little n is greater than n, then p sub n is in the neighborhood of epsilon around p.
Right, so given any epsilon, right, given any epsilon neighborhood of p, right, there's a time beyond which everybody lies in that neighborhood, right? There's a time beyond which everybody lies in that neighborhood. Okay. Well, generally you can think of, there's a last bad time. You can find a last bad index. Okay, so there exists a final bad index beyond which all times are good. Okay. Okay. So we know that for p, and we're hoping to show it for p. I'm sorry. We know that for p sub n. We're trying to show it for p sub n sub k, right? So so how do we find the k, right? So fix epsilon. We want a capital K such that when you're past capital K, p sub n sub k lies in the epsilon neighborhood of p. Okay. Right. We know there exists an n. There exists a time past which n sub n implies that p sub n lies in n sub p sub k. Right. So how do we choose our k? How do we choose our k? Right? We know that there's some n, past that time all the p sub n's are inside. Right? We also know that here's the index, right? The subsequences indexes. They're going upwards.
I chose k equals n because you said the subsequences are always strictly increasing, right?
Very clever.
Huh?
Very clever, yes.
Okay, so that means n sub k should be at least k.
Okay, yeah.
And so then if k is equal to n, then if we have that k is greater than big K, then n sub k is greater than big N.
Very good.
And I think we're just done.
Okay, yeah. So Harrison says, well, let's take k equal to n, right? Since n sub k is strictly increasing, and sub capital K must be bigger than k, which is n. Or bigger than equal to k, which is n. Right? Maybe let's take n plus 1 just to just to get rid of that equal sign there. It doesn't make any difference at all. But, okay. Right? Right? Or simply, you don't have to be so precise about it. You could just say choose, n sub k goes to infinity. So choose k such that n sub k is bigger than n. Right? You know that these guys go infinity, choose k such that n sub k is bigger than n, right? Since n sub k are increasing, everything beyond there, all n sub k are bigger than n sub capital K, which is bigger than n, for k bigger than capital K. Whichever way you work. Right? You just need to say, well, look, at some point, since these guys are increasing, at some point they're going to go past n, right? For some index, which we'll call n capital K, which we'll call capital K, these guys are going to jump beyond n. Take that guy, right? Take that as our K. Take anybody beyond there as our K, and then after that, everybody's past n, and so lying inside here. Okay. So in any case, fix an epsilon. We're trying to find the k beyond which the pn sub k's are in there, and so however you do it, you get that. So p sub n sub k lies in the epsilon neighborhood, and we're done. Right? Because all those n sub k guys are beyond the nth index. Okay, everybody all right? Izzy?
So that means P of n converging to P means that every subsequence converges to also P?
Mm-hmm.
Okay.
Yeah. Yeah. Okay. Any questions? Yes, Ali.
It says at the bottom, all n sub big K is greater than n sub little k. Is greater than n.
That should be the opposite. Little k, big K. It's hard to tell the difference. Okay. Okay, so subsequences, right? What will be important for us is the following theorem that sometimes goes by the name of the Bolzano-wire stress theorem. Namely that if you have a sequence in K, in some set X, if that set is compact, then you're guaranteed a convergent subsequence. Okay, so this is there's a related definition that says we call a space X sequentially compact if every sequence has a convergent subsequence. Okay, so wait, so so for example, like if I look at the interval 0, 1, do you think that that's sequentially compact? Do you think every sequence has a convergent subsequence? The answer is no. So you could think, our usual example, 1 over n, right? As usual, right? That guy, is an infinite sequence, but there's no subsequence of it that converges, right? Okay. And in fact, so what this theorem says is that if you're compact, then you're sequentially compact, right? So that's what this says. Yeah, compact. Compact implies sequentially compact. It is true in the context of metric spaces that the opposite is true, that sequentially compact also implies compact. Okay, but the proof of that is a little bit involved, and so I'm not gonna give that. But just know that it's true. Okay, so we're only going to prove the easier half of that. Okay, but what this kind of gives you a sense of is that what this might hint to you is that sequences are able to detect properties of the space. Okay, so like instead of thinking in terms of open covers, you could just as well think in terms of sequences and subsequences. Okay. So in fact, there's another book that in fact just ignores the topological compactness, the open cover compactness, and just goes directly to sequential compactness and goes from there, which is that's one way to do it, but then you don't know what topological compactness is. Okay. Okay, I'm going to let you think for a minute or two about how you might prove this. I think it's probably within your grasp. Let's think about an infinite sequence in a compact set. Why must there exist a convergent subsequence? You could probably get it. I could give it on the exam, and you'd be fine, right? So just think, like, do you know anything related to this? You know something related to this. Turn to a neighbor and say, yeah, we're going to use this theorem.
Okay. Oh, wait. So what's
Is it That's true. But is it Kiesel's? Okay, so ignore me. Active light closed. Yes. That's it. We'll have to slice it slow. That's fun.
Like there's a if you take a limit point, which is like the end point, like you know that there's an infinite amount of elements in every neighborhood you draw around that. So you make a sequence of just like decreasing smaller neighborhoods.
These are 100%
Like this is like 1 over
Dang, that would be like
something. So like, because you can any neighborhood you draw around point, there's an infinite number in there. So I think you can just like construct.
Yeah, but they're compact. So that's just fun.
Okay. What theorem are we going to invoke? Anybody have an idea? You've got an infinite sequence, right? So you've got this compact set, right? You've got an infinite sequence. Well, there's sort of two possibilities for the infinite sequence, right? It may have like finitely many values, right? Or it could have infinitely many values, right? They don't have to be the same. They don't have to be different values. They might all be just one. For a sequence, it might just repeat, right? Okay, so we do have to deal with sort of two cases. So case, so finitely many values, and case infinitely many values. Infinitely many values, right? Well, suppose your sequence takes only finitely many values. Like there's 3 values, or there's 2 values. Okay. Why are you guaranteed a convergent subsequence?
Like the pigeonhole principle.
Pigeonhole principle, right? Right, you've got infinitely many pigeons, and you've got only 2 holes. One of the holes must contain infinitely many pigeons, right? And so take that hole and just take all the indices for that hole, and that's your convergent subsequence. It's a constant sequence. Right? It's a proof. Pigeonhole principle. Okay, right? So if I have only finitely many values, one of those values must be attained infinitely many times, right? So take that, and take all the indices, and that's your put them in increasing order, and that's your that's the guy. Okay, so now we don't have that, but we've got infinitely many values inside of a compact set. What do you know about infinitely many values inside of a compact set? Rishi, this time.
We can get a limit point.
There's a limit point, right? So infinite set in a compact set implies there exists a limit point. P. Okay, so being a limit point means that every neighborhood contains infinitely many values. Values. Okay, so then you just constructed. Does anybody want to sort of lay out how you might construct it? Right, you've got this P, and you know that every neighborhood contains infinitely many values. Right, so somebody knew. So I'll take a neighborhood of radius 1, and how do I get a point inside there? Not you're sure you count as new. Or you, not you either, what? Anybody? Rudica, do you want to do? No? Charlotte? No? What? Matthew? Matt?
I'm gonna just have it show. Or I think I have an idea, but I'm not really sure.
That's okay. Yeah. So like, how are we gonna, do you want to construct the whole sequence, or do you want to just like, how do you know, first off, how do you know that there's a point inside this radius one ball here?
So I'll be completely honest, I was thinking of kind of using like potentially an epsilon delta proof, but I don't really know exactly where to go with that, so
Okay.
I'm not exactly sure.
Okay, that's all right, that's all right. Okay, I'll, who had, okay, go ahead, Izzy.
Okay, so just a guess, what if we take a point, just any point
Yeah.
in this neighborhood, and then you take half the radius, then you
Yeah.
take another point, and you
Yeah.
take half the radius, you just take another point, and you just keep going down?
That'll do, and the only thing you have to worry about is that the indices have to be increasing.
Mhm.
But you don't have to worry about that, because you know there's infinitely many values inside each guy, and so you can definitely choose one that's beyond your finitely chosen previous index. Right. Right. So that's the thing. So you say, okay. Right. So for each n, choose p, so for each k in n, choose p sub n sub k such that 1, the distance between p sub n sub k and p is smaller than 1 over k, and 2, n sub k is greater than n sub k minus 1. Right. And you know, this is possible because of this fact here. Right? Every neighborhood contains infinitely many values. Right? So when you take your 1 sub k, epsilon to be 1 sub k, you know there's infinitely many values in there, and so you can definitely choose one who's got a greater index than your previously chosen index, right? And so that does it for you. Then n sub k are increasing, and you know, the distance goes to 0. Right, which is the same thing as saying that they converge. Any questions? Yes, Harrison.
I do want to make sure I have like a fundamental grasp of convergence right. Okay, if I rose my hand, I would have said something wrong.
Okay, let's hear it.
Okay, so the thing was, I was thinking since P's a living point, all neighborhoods have, you could take like any radius, right?
Yep.
And there would be infinitely many points in that neighborhood.
Yep.
And all we need for convergence is that for any epsilon, right, we have if n is greater than n, then all points of that sequence.
That's where things go wrong. All points beyond that. But anyway, go on.
Okay, and so you can construct a subsequence of only points in
Okay.
there, in that neighborhood.
So you construct the subsequence. How How do you construct the subsequence?
Oh, I see.
You need to specify how you construct the subsequence.
See.
Yeah. So I guess maybe you're thinking to say something like, restrict yourself to only the points that are in that subsequence,
Yes.
only in that neighborhood,
Yes.
and then
Oh, and then you can like, okay, then you'd be able.
then you still need to construct the
I see,
subsequence.
I see.
Yeah. So not so. You're not far off. You're not far off. Yeah. Just you need to specify how it's done. You're thinking more in terms of points rather than sequences, but you have to think in terms of like, you know, this. You have to think more in terms of the sequence.
Okay.
Yeah. Yeah. You're thinking more like what we were doing earlier. Yeah. That's okay. That's okay. Okay. Other questions? Are you guys okay? Yes. Okay. Good. Good. Okay. So the next very important topic is the notion of a Cauchy sequence. Cauchy sequences. So it's sort of like sequences which really should converge. Okay. So let me give the definition. Again, you have P sub n, a sequence in metric space X, and we call the sequence Cauchy, or maybe I should probably say a Cauchy sequence. We call the sequence a Cauchy sequence if it satisfies this property. So given any epsilon, there exists a time such that if you've got two values beyond that time, then the distance between those two values, the distance between if you have two indices beyond that time, then the corresponding values are within epsilon of each other. So it's sort of like convergence, but no limit point, right? Like, there's no limit point expressed in this definition, right? We don't talk about the limit point. We just say the guys have to get closer to each other, right? We say, given any closeness, there's a time beyond which everybody is that close to each other. Okay, so for example, the usual example, 1 over n in 0, 1 is Cauchy, right? Because the values, right? If somebody says, I want you to make these guys, within a half of each other, you can find, past time 2, everybody's within a half of each other, right? To make them within a third of each other, well, past time 3, everybody's within a third of each other, and so on and so forth. So I can make these guys arbitrarily close to each other. So this is a Cauchy sequence, but it's not a convergent sequence, right? Because there's nothing to converge to in 0, 1. Yeah, Ritka.
And it's not like about adjacent pairs, it's like
No.
any 2 points.
Any 2 points, yeah. Everybody must be close to each other. Okay, everybody. Okay, so you can see why I'm kind of calling it like convergence, things that ought to converge, right? You feel like that ought to converge. The only thing that's stopping it from converging is that there's nothing to converge to, right? There's this hole there, but you feel like it really ought to be a convergent sequence. Okay. So that leads to, just sort of give the punchline at this point. Yeah, maybe. Okay, so like that leads to the definition: if in any metric space, all Cauchy sequences converge, then we call the space complete. We call the Cauchy the space complete. Okay, so so in that sense, right? In a complete metric space, Cauchy is the same thing as convergent, right? I'm just stating the definition, basically. That's what the definition says. Complete means that Cauchy is equivalent to convergent. Okay. Right, so it's another way of thinking about convergence if you're in a complete metric space, but not otherwise. Okay. Exercise maybe? I don't know. Convergent implies Cauchy. Okay, turn to a neighbor and say, of course it does. Right, and then say, because convergent means this sort of thing and Cauchy means that sort of thing, so don't necessarily give a rigorous proof, but give the idea, right? Like, what does convergent mean to you? What does Cauchy mean to you?
So, like, if I'm taking everything is epsilon, but it's saying for a different epsilon after everything is
So you really don't look at
delta that, which is we just want the delta. So for all of the same epsilon. You know what I'm saying? But it's like somewhere. Doesn't have to be the same. You know what I'm saying? Yes. Like in a neighborhood.
Okay, so what's the picture, right? What's the picture for convergent? Right, here's the time. If you converge to some point, right, that means that given any epsilon, there's a time past which everybody lies inside the ball, right? What does Cauchy mean? Given any epsilon, there's a time past which everybody is close to each other, right? So, right? Who can finish the sentence? So, if everybody is inside the ball, then
the distance is at most 2 epsilon.
Right, everybody is within 2 epsilon of each other. So take the epsilon over 2 ball, maybe if you want to be improper about it, right? Take the epsilon over 2 ball. If you're actually writing a proof, then you'd say, given epsilon, we know that there's a time past which everybody's in the epsilon over 2 ball, right? And then so beyond that point, all pairs of points are within epsilon of each other. End. Okay, but you see the idea, I hope, right? If you're close to P, then you're close to each other. Right? That's it. Should I write that down, or do people feel? Close your eyes for a second. Should I write that down properly? Okay, fingers down. Okay, a couple people wanted it, so want to show that for all epsilon greater than 0, we exist in n, such that if n and m are greater than it, then the distance between p sub n and p sub m is smaller than epsilon. Since p sub n converges to p, we know that there exists an n past which all p sub n lie in the epsilon over 2 ball of p. But then the distance from p sub n to p sub m is going to be smaller than the distance from p sub n to p plus the distance from p to p sub m, which is smaller than epsilon over 2, which sums to epsilon. But then for n bigger than capital N, questions? Okay, so let me give just a sort of slight geometric rephrasing of Cauchiness. And this is not anything serious at all. We make the following definition. So given a set E in some sort of X metric space, let diam E denote the supremum of all sets of distances for pairs of points inside your set. Okay, so you got some set, and you start picking points at random, right? You take all possible pairs of points and look at the distance between pairs of points. You create a set of distances. Okay, this set is just a bunch of distances, right? And it's a set that's contained in R, right? A set of real values, right? So either it's bounded or it's unbounded. So if it's unbounded, then this is infinite. If it's bounded, then there's some supremum for it. Okay, and that thing is called the diameter. So it's just the greatest distance between pairs of points, roughly speaking. Right? So we simply bound for distances between pairs of points in E, which is what it said already. Okay, so now recall Cauchy means that, right, given any epsilon, there exists an n such that when you're past that, then you know that the distance between the corresponding points is smaller than epsilon, right? So given any epsilon, you can find a time past which everybody's within epsilon of each other, right? And you can do that for any epsilon, no matter how small, right? So in terms of diameter, what's Cauchiness in terms of diameter? So rewrite this in terms of diameter, right? Diameter says, you look at distances between pairs of points, take the greatest of them, and that's the diameter. How do we use that to express Cauchiness? Turn to a neighbor and say, I don't know.
Yeah, I'm saying like E is the set of all the points in the sequence
That are bigger than that.
distances of all the pairs.
But that we smarted up some.
And so then I think leaving everything else as it is fine.
Speculation.
Okay, anybody want to make a guess? Allie? No? Izzy is pointing at you. Michael?
I'll just say that you let E be the set of Pn for all n bigger than big N, and then you want the diameter of your set E to be less than epsilon.
Yeah. So, right. So, let's see. If we let E sub n denote the collection of points P sub n and P sub n plus 1, right? The tail, right? The tail starting at point n, right? So we're given any epsilon, we want, right? So this is saying, given any epsilon, we want n such that if you're past that point, then the diameter of E sub little n should be smaller than epsilon, right? Right. But thinking of this thing as a function, what you're really saying is that the limit of the diameter of E sub n as n goes to infinity is 0. That's exactly the same statement, right? Given any epsilon, we know diameter is positive, right? Diameter is greater than or equal to 0, right? So given any epsilon, we want n such that we can make this thing within epsilon of 0. In other words, what we're saying is that the limit of this function is 0, right? That's exactly the same statement. Okay, so this is the geometric rephrasal of Cauchiness. Does that make sense? Does that make sense? Right? This is basically, do you remember what the definition of limit means, right, for a function? Or for, I guess this is a sequence. Okay. Okay, a couple of facts about the diameter that we're going to need. So, one, the diameter of the closure is the same thing as the diameter of the original. And two, if you have K sub n, a sequence of nested compact sets in metric space X, if you have further that the diameter of the K sub n is 0, then the intersection of the K sub n, what am I going to say?
Should that be the diameter goes to 0?
I'm sorry, yes, thank you. What am I going to say? Then the intersection you have a bunch of compact sets. Infinitely, the diameters of them go to 0. You take the intersection of all of them, and is that it?
It's the empty set? Or
You're close.
It's the limit. Sorry.
You're close. It's not the empty set, but it is like
This is the smallest one?
the smallest one. Well, the diameters go to 0. There is no smallest one, right? Not necessarily, at least. Yeah, Rishi.
It's just a singleton?
It'll be a singleton. It will be a single point. Okay, let's start with that one, because I thought that one would be easy, and yet I see a lot of sort of wrinkled brows. So, do you remember something related to this? Like you've got nested compact sets, right? You take their intersection, and you're guaranteed that their intersection is non-empty, right? Because of the finite intersection property. Remember the finite intersection property that every finite collection has do I have to say non-compact? I mean non-empty. Maybe I have to say non-empty just to be careful. So, right, maybe that's the cause of the wrinkled brows. No. This reminds me of when Professor Conway turned around and there was something wrong with what he had written, and he said, "So that is why you all look so stupid." Yeah. Anyway, yeah. No, that was just Conway. Yeah. It didn't mean anything. That's just how he was. So, right, finite intersection property, remember you've got a bunch of sets such that the intersection of finitely many of them is never empty. And then if they're compact, then you know that the infinite intersection is also going to be non-empty, right? So here we've got nested non-empty compact sets, right? And so we know that they're going to satisfy the finite intersection property, right? Because any finite intersection will simply be the smallest one of them, right? Any finite intersection will be the smallest one of them. So they satisfy the finite intersection property. Then the infinite intersection contains something, right? It must contain at least one point. But it can't contain 2 points, because if it did, then the diameter wouldn't go to 0. Okay. So that's the proof. K sub n satisfy the finite intersection property. And so the intersection is not empty. The intersection cannot contain 2 points, right? Cannot contain more than 1 point, right? Else the diameter would be, you know, bigger than or equal to the distance between those 2 points. Right. So, okay. Okay. Is that okay? Is that all right? Okay. Let's do the first one. That the diameter of the closure equals the diameter of the set itself. Proof of 1. Okay, so you already know that the diameter of the closure is bigger than or equal to the diameter of E. Right, that's for sure, because every pair of points in E is a pair of points in E bar. Right, so you need to show the other direction. Okay, so pick any 2 points. Well, first off, why does this seem pretty likely to be true? Why is it sort of intuitively true? Rishi.
Well, since the closure should be like sort of tightly packed around our original set, we shouldn't be introducing any new pairs of points that are further away than we could before.
Yeah, the only things that we're introducing are limit points, right? And what do you know about limit points? Well, they're infinitely close to points of E, right? Infinitely, they can be arbitrarily well approximated by points of E. So that's basically it, right? So pick any. So this is sort of intuitively obvious, right? So pick any 2 points, P and Q in E bar. Okay. And then choose for any epsilon, we know that there exists P prime and Q prime in E, such that the distance between P and P prime is smaller than epsilon, and the distance between Q and Q prime is smaller than epsilon. Right? So this is the well approximating business, right? Either P and, P might be in E already, but that's even better, right? We know that there's somebody in E who well approximates somebody in E, that's for sure. If it's a limit point, we know that there's somebody in there that's close to it, right? So what does that tell us? Then the distance between P and Q is controlled by the distance of P to P prime plus the distance of P prime to Q prime plus the distance of Q prime to Q. Right? And so we see that it's smaller than the distance of P prime to Q prime plus 2 epsilon. Actually let me just make these half epsilons and make this a plain old epsilon, as usual. It doesn't matter. As you see, it doesn't matter at all. Okay, so what does that tell you? That whenever you have a pair of points in E bar, there's another pair of points in E whose distance is, at most, is, right, so that this thing is controlled by that distance plus epsilon, right? Okay. Then, if we take supremums over both sides, taking supremums, we see that the diameter of the left-hand side is controlled, is less than or equal to the diameter of this thing on the right-hand side plus epsilon for any epsilon. Right? But for that to be true, we must have, oops, this should be diameter. We have this. And that's what we wanted. Yeah, we should.
If we, once we get there, do we even need to use the like other direction? Can we just say that, well, if they can get, if this is equal to that plus epsilon for any epsilon, can we just like say that, well, if it's arbitrarily close, it should be equal?
Well, all we have is an upper bound here, right? So, no, you still need the other. You still need the other direction. Yeah. Okay. Okay. So now we've got the lemmas, and we're just in time. I think we'll be able to get where I wanted. Unusually, we will actually do everything that I intended to do. So, we have the following theorem that any compact metric space is complete. Okay, so what's the proof? We're just going to kind of put things, use the lemmas will give us the proof. Let P sub n be a Cauchy sequence. What should we do next? Right? We want to show that P sub n converges to some value P. How are we going to get that value P? Talk with the neighbor. Talk with the neighbor for 1 minute. Michael, you can definitely do this one. Yes, absolutely. Because of something you said not a few minutes ago. The hint is use the geometric characterization. Okay, let me, because now we're starting to run out of time. Let me actually start you off on it. So we know that if you're Cauchy, then the diameter of the tails goes to 0, right? So we're hoping that we can get some point out of the diameter of the tails, out of the tails, right? Where should that point be? How do we get that point?
Do we just take the intersection?
We take the intersection. but when we take it, maybe,
I guess we need to make them close compacts, these are closures.
exactly. So it may be when we take the intersection, we get nothing, right? But if we take the closure of them, because they're closed inside the compact metric space, they become compact. And now we've got nested compact sets. And so the intersection is now non-empty, right? And consists of a single point. That's the point we're looking for. Okay, so let me write that down, right? P sub n closure, these guys are a nested sequence of compact sets, non-empty. Right? And so we know that the intersection consists of a single point, right? With diameters going to 0, right? Because the diameter of the closures is the same as the diameter of the original. So we do need that first fact, right? The diameters of the closures also go to 0, right? So the intersection consists of a single point, right? The intersection consists of a single point, P, right? And so then, given any epsilon, we know that there exists an n such that if you're past there, then the diameter of P sub little n closure is smaller than epsilon. Right? But then, for all k for all n bigger than capital N, the distance between P sub n and P is smaller than epsilon. And that's what you're hoping for. Okay. Yeah, I see.
What's E again? Is it just E some set in a metric space, like X or something?
E was the tail. This thing, you mean P sub n?
Oh, yeah.
P sub n, P sub n plus 1. Sorry, yeah, that might have been too much notation. Yeah.
Oh, never mind.
Okay. Yeah.
We're talking about the closure of E sub n
Mhm.
and not the closure of E sub n, if that makes sense. I guess, never mind, it's, yeah.
Yeah, the closure of E sub n. I don't know how I should write that. Okay. One final corollary. Euclidean space is complete. So, given a Cauchy sequence, why is it complete? How do I know that this is a corollary of the earlier guy, right? So we know that any compact metric space is complete. Euclidean space isn't compact, but if we got a Cauchy sequence in Euclidean space, then Harrison?
All of it lies in a K cell.
Exactly, right? The Cauchy sequence, because of the shrinking diameter business, right? Past we're guaranteed that it's bounded, right? It's bounded, right? sequence being Cauchy means that it's bounded. So sits in a K cell, right? And we don't really even need that, right? So it's bounded, so we know that it lives in a compact set. So sits in a K cell, which is compact. Right? And then you're done. Okay, you have 1 minute extra. Hey, yeah.
So, our next picture.
Okay.
What are we going to cover like roughly around the 2 chapters again, like on the exam?
Let's see.